Hi everyone, welcome to the 7th episode of my tutorials on Nextflow for bioinformatics. In today's video, I'm going to show you how to write a Nextflow script to perform genome assembly with Flye. Now, for those who don't know, Flye is a tool that is used to assemble long-read data. So you can use it to assemble Oxford and Newport data. You can also use it to assemble Pagberry data. Now, I've already made a tutorial where I showed how to run Flye on the command line. So for this tutorial, I'll show you how to include the command to run Flye in a Nextflow script or a Nextflow pipeline. You can also download the Nextflow script we are going to use. So check the description box, you'll find a link to the Nextflow script that I'm going to use for this exercise. So let's proceed. So for this tutorial, you need to make sure that you have Nextflow installed and you should also have Flye installed. I have tutorials that show how to install these two. So check the description box, you'll find links to those videos. Now let's open the terminal and then start the exercise. Okay, we have opened the terminal. So what I'm going to do first is to create a working directory and then I'll cd into it. So I'll say make the Nextflow. You can use any name of your choice. If you are using it for a project, then you can also use the project's name as the name of the directory. But I'll use Nextflow because it's a Nextflow tutorial. And then I'll cd into it. Yeah, so now I'm done. All right. Now we need to get an example data we will use for this exercise. So I already have one. Let's check it out. So visit this page and you'll find the file that we are going to use. So we are using an Oxford and Newport data. Now, in case you are not able to visit this page, you can just use this session ID here. I'll paste this in the description box, by the way. So you can also visit ENA, this database, and then just paste the session ID here. Again, this session ID, you can find it in the description box. So you can just paste it and come to view. So when you click it, you have access to the file. All right. So that's how we do it. Now we need to download it. So I'll just get the file, which is here. Let's check it. So I'll download on a terminal. So I'll just right click and get a download link. So I'll just right click and then get a download. So I'll just copy the link. You can also download with your browser. That's fine. But if you're working on a terminal, things are faster when you do it on the terminal. So I'll just move to the terminal and then download it. So I'm here. So I'll do this. I'll just use wget and then I'll paste the link there like this. All right. And then I'll download it. So let's download the file now. Okay, so the file has been downloaded. So it's 124 MB, so it should be done very soon. Okay, the example data has been downloaded. So let's do an ls and we are going to find it here. So there's it. Now this nanopore data here, it's a table. It has been compressed. So that's why I have .star.gz. So we need to decompress it so that we can get our file itself, the FASTQ file. So to do that, I'll just say xbfz and then I'll say all-fastq.star.gz. That's the file name. All right, so let's execute this command. So once we do that, the file will be decompressed. So now you can do an ls and you find it there. All right, so there's it. So the original file, the compressed one is still there, but what we've done is to extract the contents to get this one here. So this is what we are going to use. All right, so let's clear the screen and do something else. Let's do an ls and proceed. Now, if you have your files, it's advisable to organize them properly. So if you have FASTQ files, you put them in one directory and then the others will be in other directories. So I'll create a directory called FASTQ. So I'll say make the FASTQ and then I'll move this FASTQ file there. So I'll say mv and I'll move it there. So the file name, and then I specify the directory where I want to move it. So it's gone. Not gone per se, but it has been moved to the FASTQ directory. So do an ls, you'll find your FASTQ directory, ls into it, you'll find your actual FASTQ file, which is here. So now we have the data ready, so we can proceed to perform a genome assembly. Now, before I proceed, let me say that this is a raw nanopore data. All right, so we are dealing with the raw reads. So ideally, what we should have done was to perform quality control to assess the quality and also remove adapters. All right. But for the tutorial, I am showing you how to perform the genome assembly itself. I'm showing you how to include the genome assembly command in a Nextflow script. So I'm going to skip the quality control and then the adapter trimming part. That one, I've covered them in separate tutorials, so you can also check them out. For this tutorial, I repeat, I'm focusing on showing you how to include the Flye command in the Nextflow script. So I'll skip quality control, and I'm also going to skip the adapter remover. But in reality, you should do both activities before you perform the assembly. So that is the disclaimer for this tutorial. All right, so let's proceed. So if you are going to run your Nextflow command, you also need to take note of your directory, your working directory. So I will say pwd, I'll have it there. You also need to get the directory which has the files of interest. So in this case, it's FASTQ. All right, so I'll need the directory. So I can get a full path of the directory by saying rel path FASTQ. So this will give me the path to the FASTQ directory. All right, this command may not work if you're using macOS, but you can also do this. You can also cd FASTQ and do pwd. All right, that will also give you the directory like this. All right, so just try any of them, that's fine. Now I'm going to cd back because I have cd'd into the FASTQ directory. So I'll just do a cd // and I'll come back. All right, so I need to make sure I'm here, pwd. I need to make sure I'm here so that when I do an ls, I'll see my FASTQ directory, and I'll also see my original file, the one I downloaded. So this should be it. So now we can proceed. So let's clear the screen and then continue. Let's do an ls again to check our files one more time. ls FASTQ rel path. Let's do some revision. Perfect. All right, so we have it. So now we have this directory which we will use, and then other stuffs I will let you know when we are writing the scripts. So let's open the Nextflow script and then work in it. So that means we need to open an empty file, a new text file basically. So I prefer to use Nano for the editing of files, but you can also use VinI or Vim or any text editor of your choice. That's fine. All right, so that's what you need to know. So I will open my new file now. So I'll say Nano, and I'll say assemble.nf. You can use any name of your choice, that's fine. Maybe you want to use pipeline or anything, that's also fine. So just use any name of your choice to name your file. I'll open it, so now I can start. So I'll proceed now. Now before I proceed, let me say that the default behavior for the current version of Nextflow I'm using is to use the DSL version 2. So I will not specify it here. That's the default version. But if you want to use another version, you will have to specify it. There's a page that shows you how to do that. So check the description where you'll find the link to that page. All right, so we are here now. So that's what we are going to do. We need to first get the files. So I think I'll open another terminal. Yeah, open another terminal here. So first of all, I'll do an ls into the FASTQ directory. All right, I see my file there. Now let's do this. In Nextflow, it's also important you know your way around Linux. That means Linux commands, because you are doing bioinformatics analysis, you will obviously use some Linux commands. So these commands, Nextflow will take them and then use that to get the necessary information, necessary files. All right, so I'm going to supply Nextflow with the directory which are the files. So whatever we are going to use, you can apply it if you have multiple files or multiple samples. That's fine. All right, so you don't need to worry. Even though I'm using just a single file here or a single sample, you can use the same approach for multiple files. All right, so let's do this. So if let's say I want to get the FASTQ files in this directory, all right, I need to say ls FASTQ, and I can say star.FASTQ like this. All right, now let me also bring this to your attention. So for the FASTQ files, ideally you should compress it, but I did not compress it. Okay, but if you have multiple files, it's important to compress so that you can have the space that your files are taking becomes smaller. All right, so make sure you always compress your files. So in most of the situations, you may see the FASTQ files as .fastq.gz, but for this tutorial, it's .fastq. So that is why I did ls fastq/star.fastq. So if you have your own data, then you need to make sure that you look at the extension and then use the appropriate extension. So if yours is .fascio.gz, they have to specify ls fascio/star.fascio.gz. It's important to take note of that. All right, so I'll need that. So because I'm going to run it in Nextflow, I need the 4 parts. All right, so the command will be something like this: ls/home/cobana/nextflow/fascio/star.fascio. So this will give me the files. All right, so I'm going to issue something similar in Nextflow. Okay, so let's go back to Nextflow. So this is what I'm going to do. I'm going to say params.fascio. Let me just put it this way. And I'll say equals, I'll bring my double quotes, and I'll say /home/cobana/nextflow/fascio/star.fascio. Remember we did something similar here. Okay, so here I added ls, but in Nextflow we don't need to add ls. We want the file themselves, so Nextflow will take care of the rest. So I need this. So this means all files that end with .fascio should be made available to Nextflow. That's what this means, basically. So we have our fascio files. So now let's proceed. So let's do this. Let's scroll down. Now we have everything we need. So what we are going to do next is to create a process. So a process is a task. All right. Now, if you are going to analyze nanopore data, let's say if it's a bacterial genome data, then you perform QC, you perform trimming, you perform genome assembly. All right. So all these are tasks. Genome assembly is one. That's what we have been doing. And so you define tasks, and in Nextflow we call them processes. All right. So this is what I'm going to create a process. So I'll say process, and I'll say assembly, because I'm going to perform assembly, genome assembly. And then I'll bring my curly brackets, the first one, and then I'll bring the second one here. So in between the curly brackets, we will put our command for this process, this task, assembly. That's what you need to know. So let's start. So first of all, I'll define my inputs. All right, so the inputs, I'll do this. I'll say inputs, colon, and then the next line, I'll specify something. So I'll type a space and I'll say path, and then I type a space. So I've done that. Let me just do it again. So I'll type in path space, and then I'll specify an alias. So this will be the placeholder for all the files in that directory. You know, the other files that will come in as a result of this command here. So I'll just say fascio. And then the next line, I'll say outputs. I'll bring a colon, a space, and I'll say path again. I bring a double quote, I'll say star, another double quotes like this. I have that here. All right, so that is done. Now we need to do something else. So this star here means all outputs. We need it. We need to have access to. We want to have access to all the output files. That's what the star here means. Path. Now the next line we'll add a script. So here we start with 3 double quotes, another 3 double quotes, and in between we'll put our command. So this is where we'll place our Flye command. So we are going to do that now. So let's input our Flye command. So first of all, let me just do this. Let me type Flye here again. I think I'll open a new terminal here first. I'll just type Flye to get the usage. So with Flye, we have the usage. So you call Flye, you specify the data type, and then you specify your output directory. You also have to specify genome size, threads. There are options here. So some of them are mandatory, some of them are not, but I'll show you how to use some of them. So we are basically doing a basic genome assembly. All right, so let's do this. So we will call Flye, and then after calling Flye, what do? We will say --nano-raw. We are using a raw nanopore data, and then we will specify the file. So this is where this one comes in, the fascio. So I'll say $fascio, and then space, and I'll specify the output directory. So the output directory we specify with this or this. I'll use this one because it's shorter. So that'll be -o. And then the output directory, because you may be dealing with multiple samples, you have to do this. That's what I do, by the way. So I'll just use the sample name minus the file extension. So in this case, the output directory is going to be all_min. That's what it's going to be. So if you have a different name, you can also use that name. But I'll show you how to remove the extension. So that's what you are going to do. So we will do this. So that's what we do. So you can do this. You can say $, and then you bring your curly brackets, and you can say Pascal, and then you can say .simple name like this. And then you bring your curly brackets again. So what will happen is that this one, let's go back to our file. So it will remove the .pascal, and you have your sample name all_min. So that's how we do it. Now, if you're using .pascal.gz, then the command will slightly change. If you are facing a situation like that, you can always contact me and we can have a session together on that. So that's it. So this is the command. Now let's add something else. Let's check again. With Flye, you can also specify the genome size. So that one, you can use this Flye. You can also use -gen. So I'll specify a genome size. All right. So I'll say -gen, and I'll say 5.9 for the genome, and then I'll say M. Yeah, let me just do it again. Let me just repeat again. So to specify the genome size, you can say -gen. So -gen here can be used in place of the -genome-size. All right, that's why I'm doing it. And then I'll specify the genome size. So I'll say 5.9 M. Now the genome size, you need to know the organism you are dealing with, and then you can get a genome size. So for this data we are using, it's a Mycobacterium ostrans data. It has been indicated here. Okay, so Mycobacterium ostrans isolate. So the genome size is 5.9 M. All right, that's why I'm using it here. 5.9 MB. Yeah, so 5.9 MB. Yeah. So that's why I'm specifying that here. So if you are using a different sample, then you should know the size of the organism, then you can use that appropriately. So that is fine. Now let's do something else. So you can also specify threads to make it run faster. So if you're using a Linux cluster, an HPC system, you can increase the number of threads. So you can say that's T. So instead of --threads, which is here, let's check. You can say that's T. That's what I'm using here. And I'll say 6. All right. I'm using my normal laptop. That's why I'm using 6. But if you have more cores, you can increase it to make the process faster. And then with Flye, it also does polishing. So that one, you can specify using the iterations here. So iterations, and you specify. So 1, 2, 3, up to the maximum. You can check the documentation. You find the maximum number of iterations you can do. But for this tutorial, we will keep it simple. I'll just use 1 because I want to show you how to specify it. So I'll say space, and I'll say -I, and I'll just say 1. All right. So Flye has a default number of iterations it does. So if you want to specify, or if you want to change the default number, then you bring your -I and you specify the number. All right. So for it to, I'll just indicate 1. That is it. So this becomes the final command for Flye. Now with what we've done, this is a basic Nextflow command. So sometimes you may want to add some additional information. For example, you may want to customize, or you may want to change number of threads depending on your system. All right, so you can include that in the Nextflow command. You can just set some params here and then feed that, so that you don't have to come into the code itself to change the threads or maybe iterations or genome size. So it's possible to do all of these things. All right, so you can have the main code here in the scripts in this session, and then those things that you think will be variable or may change depending on the user or whatever, then you can add those ones as params, or you can even create a params file, and then you can specify that when running the Nextflow script. But we will talk about that in another video. So for now, we are keeping it simple because I want beginners to also understand how to use Nextflow. So this becomes our final command. So now we are done with the command. So let's just clear the spaces here. Let's make sure we have our curly brackets here and then here, and then in between we have our commands. Now we are done with the process itself, the creation of the task, the assembly. Now we have to also call it. So to do that, we have to come here and then use the workflow. So we say workflow, and then we bring a curly bracket again, and then another curly bracket somewhere here, and in between we can add our final command. So let's say finishing touches. Let me just switch that way. So if you have a process, in order for you to run the process and perform the analysis on the specified data sets, then you need to also create a channel or channels, depending on how many data you have, how much data. So here we are supplying FASTQ file. That's the only information we are supplying now. So we need one channel. So I'll specify that here. So I'll say FASTQ _ch equals, and then I'll say channel dot from path. I bring a parenthesis and I'll say params dot FASTQ. You know, we created a params here. So that is what we are bringing here. Like this. And then after that, what do? We just close it. And then when we call the process, this one here, we specify the channel as well. So we'll call the process now assembly. So I'll say assembly, and then I'll say FASTQ _ch like this. And then I also want to display the outputs, the output that will be generated. So I'll bring another command here. So I'll say assembly.out.view like this. So this becomes the final command for Nextflow. Now let's make sure everything is in order, and then we can run it. So I have everything done. I have my channel created. I've called the process. I've specified the inputs, which is the FASTQ. I've also specified the output here, so to view it. So this becomes the final Nextflow command, or let me just say the final script, because we now have a script. So let's exit and save changes. So I will save the changes and then I'll exit. So if I do an ls, I'm going to find my Nextflow script here. So now I'm going to run Nextflow. So I'll run Nextflow and then I'll supply it with the script here. So I'll say Nextflow run, and I'll say assemble.nf. So let's execute this command. So once we do that, Nextflow will start its work. So we have to wait for everything to get done for us. Take note that the assembly process is computational expensive, so it can take some time. All right, depending on your computational power. So you have to be patient for everything to get done for you. Okay, Nextflow has completed its work. So for me, it took about 20 minutes for it to get done. Take note that the time will differ. All right, so it depends on the computing power you have. So the time that Nextflow takes to complete the work will be longer or shorter than what I have. So take note of that. All right, so the output, we have it here. There's it. All right, so that means that if you do an ls into this part, you will see the output, which is this one here. So there's the output. Now if you do an ls, you will see work. So there's the directory which Nextflow saves the outputs. That's the default directory, the default settings for Nextflow. So if you ls into it, you'll find another subdirectory. You have to ls into it again. You find another one, and then it goes like that till you see your file. All right. So till you see your file or your output. So mine is here. So I'll have to ls into that, and then I'll see the outputs. I have them here. Now, if you look at this, it can be complicated, especially for beginners. You have to go from one directory to the other. So it can be complicated, especially for beginners. So there's a way to go around it. There's a workaround. So that's what we are going to look at next. Let's just clear the screen. And then let's do an ls first. And then let's do an ls again to that directory. And so it is possible to configure Nextflow so that all the outputs, in this case, all underscore minor, is saved in our respective working directories. My working directory, if I do pwd, it's here. So at the moment, I have this, and this in it. So what I want to do next is to configure Nextflow so that the outputs that I'll get will all be saved in the same working directory. Instead of going to work/39/ all those ones, I'm going to configure so that I have everything just in my working directory. So I'll edit the Nextflow scripts. Now, instead of editing, I'll make a copy of it and then I'll edit the copy. I always do that, all right, so that I have a backup of my working script so that if anything happens, I can always go back for the original script or the working script and then use that. So I'll say cp assemble.nf and I'll say assemble2.nf. So that's a copy. So if I do an ls, I'm going to see the copy. So I'm going to edit this one. So I'll say nano assemble2.nf. And then when I open it, I'll specify the directory which I want to store the outputs. So I'll do this. I'll say param.outDar equals, and I'll bring my double quotes. I'll say /home/cobana/nextflow/Flye underscore outputs like this. So this is the output directory. Now the output directory we specify doesn't need to exist. Nextflow will create it automatically and then use it. So you can see that I don't have this created, but I've specified it. So Nextflow will create it and then we'll store the output in it. All right, so let's continue. Now, after doing this, you have to come to the process itself, then add some information there. So just before you even start the input, output, etc., you just have to specify that. So we are going to use the publish that option. All right. So you will say publish that. The D is uppercase. You bring your parentheses, you bring your double quotes, $, curly brackets, and then you specify params.outDar or whatever you use to define the output directory. All right, so mine is params.outDar. And then you bring your curly brackets again to close it, and then another double quotes. And then you bring a comma, and then you say mode, and you bring a colon, space, single quotes, copy, and then you bring your parentheses again. Now here the copy, I always use copy because I want to keep a copy of the original outputs. All right, so what will happen is that Nextflow will generate the output and save them in the working directory that it creates, the work. Let me just open this one here. This one, the default directory here. All right, Nextflow will still keep those outputs in there and then make a copy for us in our directory of interest, which in this case is Flye_outputs. But if you don't want that behavior, then you can just use move. So that means it's going to move the files into the directory. So you can do this. You can also use copy. So if you have enough space, you can use copy and then just remove the entire directory when you are done with your pipeline. But if you don't have space, you can always use the move, or there are other modes as well. You can just check the Nextflow documentation to look at the available modes. All right, so that's what you need to know. Okay, so I will change back to copy and then I will use it. And also sometimes if you are using a Nextflow pipeline, maybe you have different tags and maybe the tags depend on each other. That means that the output of one will serve as the input for another. And so that means that if you have all of them in a single directory, it helps. All right, so it's recommended to use a copy, but you can always use the move if you know what you are doing, and then it will be fine. So I'll keep it this way. All right, so that is it. We don't need to change anything again. That is all that we have to add. The rest, we will still maintain them as they are. So let's exit and then save changes. All right, so I'll do an ls again just to look at my stuffs. So this is what I edited, so I'll run it, but I'll remove the directory again here, this red directory, im-fr. You can keep it, by the way, doesn't change it, but I'm going to remove it and then rerun Nextflow. So I'll say Nextflow run assemble2.nf, and then I'll execute the command. So Nextflow will start its work. So I have to wait for it to get done for me. So I'm expecting everything to get done in 20 minutes time, around that time. So let's wait for Nextflow to complete its work. Okay, Flye has completed its work. So even though we specify a directory to save the output, we will still have this display file because we made a copy. So we can create a screen and we can do an ls, and we will find the directory that we specified. Mine is Flye_output. So if I ls into it, I'm going to find my sample there, this one. So if you add multiple samples, then each of the sample will have a different directory, assuming that the samples have different names or different IDs, right? So each of them will be here, and you can also ls into them. So you can ls into Flye output, check all, and now you'll find a file there. Now, a description of the output files for Flye can be found on the Flye GitHub page. So I'll leave the link to that page in the description box. Also, after Genome Assembly, you can perform some additional activities. So these activities are called them Post-Genome Assembly Analysis. All right. So if you want to know more, you can check the playlist right here.